Good morning, cadets. We have studied Ampere circuital law in the previous session, and now we will solve some numerical problems based on Ampere circuital law. The first problem is like this: there is a wire which is especially in the cylindrical shape. A long wire is there which is carrying the current. The current is uniformly distributed throughout the cross sectional area of the wire, and the wire has a circular cross sectional area with radius A. The wire has a radius A with uniform cross sectional area, circular cross sectional area. You are asked to calculate what is the magnetic field in the region R less than A, where A is the radius. Less than A means inside the wire, and R greater than A when the distance of the point is away from the center, that is distance of the point is outside the wire and inside the wire. You are asked to calculate magnetic field. This wire is carrying current. This is a metallic wire. Okay. Now first we will calculate what is the magnetic field outside the current carrying wire. Outside the current carrying conductor we have calculated in the previous video by applying Ampere circuital law. B equal to mu naught I upon 2 pi r. This is the result, where r is the perpendicular distance of the point from the wire, right? That is r, and I is the current carried by the wire, and mu naught upon 2 pi is the constant. Mu naught is permeability of free space, right? Here the distance is outside the wire, so it is written distance is greater than the radius of the wire. So from this equation it is quite clear that if you know the distance and if you know the strength of the current, very easily we can calculate magnetic field, and it is evident that magnetic field is inversely proportional to the distance. As you go away from the wire, magnetic field goes on decreasing. As you approach closer and closer to the wire, magnetic field goes on increasing. Okay. Now what happens if the point, this point, instead of outside, if it is lying inside, if the point is lying inside the conductor, suppose the point is inside the conductor at a distance r, and this r is less than a. When the point P lies inside the wire at a distance r less than the radius of the wire, then apply Ampere circuital law. We know Ampere circuital law, B dot dl equal to mu naught IE. How do you apply? You have to draw an enclosing Amperian loop. So here you have to write, draw Amperian circular loop, right, of radius r, such that this r is less than a. After drawing this loop, now we are applying Ampere circuital law. B dot dl is equal to mu naught IE. Integral of B dot dl is equal to mu naught IE. So when you apply at all the points, you know, because of symmetry, magnetic field is tangential to this Amperian loop. So I can write it as B dot dl becomes BDL, integral of dl, closed integral of dl around that Ampere loop gives us mu naught times IE. Here the current that is enclosed in this smaller loop will not be the entire current I. The entire current that is passing through the whole conductor is I, whereas the current that is passing through this smaller circular area, I have taken it as IE, enclosed current, which is obviously less than current I. Here you can write IE is the current enclosed, by the Amperian loop. and this IE is less than I. So, left hand side gives you B into 2 pi r, where 2 pi r gives you the circumference. And what is IE? First we will calculate IE. IE is the current enclosed in this small area, circular area of radius pi r square, right. Therefore, IE can be calculated using this given thing, that this entire circular cross sectional area of the wire carries the uniform current I, total current I. So, I will write pi a square, where a is the radius, the pi a square, entire circular area of the conductor carries current I, whereas what is the current carried by this one, pi r square. So, pi cancels, you are left with I r square upon a square. So, that becomes I r square upon a square, right. This is the current enclosed. This I have to substitute in the above equation. So, integral of dl gives you 2 pi r. So, I will write, therefore, the above equation becomes B into 2 pi r equal to mu naught times IE becomes I r square upon a square. Now, this you have to simplify. So, when you simplify this, you see 1 r cancels. So, you are left with B equal to mu naught I upon 2 pi a square into, I am keeping this r separately, so that you can see pi a square is circular area of the entire wire. Pi a square is constant, 2 of course is constant, mu naught is also constant, the total current that is passing through the conductor is also constant. So, entire bracket is constant. So, B is directly proportional to the distance of the point. The distance of the point here is taken as r, which is less than radius. Therefore, from this we conclude that B is directly proportional to r. So, as r increases up to A, magnetic field increases. As r decreases from A to the center, magnetic field also decreases. At the exact center of this cylindrical axis, magnetic field becomes 0, right. Now, one more point you can notice here, what is the magnetic field on the surface? Magnetic field on the surface becomes, you can just substitute r equal to A, 1 A cancels, you are getting simple equation mu naught I upon 2 pi A, right, that is the value. So, thus we get an important result. This can be very systematically drawn with the help of a graph. So, first case, when the point is lying outside the wire, magnetic field is inversely proportional to distance. When the point lies inside the wire, magnetic field is directly proportional to r. On the surface also we can calculate what is the value on the surface. On the surface, you can write on the surface. On the surface, you see r becomes equal to A. The distance r becomes equal to A, radius of the cylindrical wire. Therefore, B becomes very simple, mu naught I upon 2 pi A, that is it, mu naught I upon 2 pi A. This is the equation on the surface. So, 3 values we got. This is 1, call this 1, this one 2, and this one is 3. Using 3 results, I can draw the graph. From the graph, it is very easy to conclude and analyze. So, using these 3 equations, I can draw the graph of magnetic field versus distance. Yes, this is distance r, this is 0, and this is magnetic field, right. When r is less than A, let us take this distance as A, the radius of the wire. When r is equal to A, we got the third equation. R is equal to A, we got the third equation. So, I will show this, yes, this as the maximum value of magnetic field. So, that is mu naught I upon 2 pi A, that is B max, right. And when R is less than A, B is directly proportional to R, means magnetic field increases linearly up to this particular point. So, it becomes straight line because B is directly proportional to R when R is less than A. From here to here, from 0 to A, when R is less than A, B is directly proportional to R. This implies the magnetic field is directly proportional to the distance. But when R is greater than A, look at this, when R is greater than A, then B is inversely proportional to R. So, this is how we get the result. B is inversely proportional to R. So, this is very important observation. When R is equal to A on the surface of the wire, B has maximum value mu naught I upon 2 pi A. So, this shows that the magnetic field doesn't become infinity on the surface of the wire, right. On the surface of the wire, we need to consider what is the radius of the wire. So, mu naught I upon 2 pi A, where A is the radius of the wire. Okay. Let us solve some more simple problems. Let us look into this simple problem. A long straight wire carries a current of 35 ampere. What is the magnetic field at a point 20 centimeter from the wire? A long straight wire is there. Let us say this is a long straight wire, carries a current of 35 amperes. 35 amperes at a distance of 20 centimeter. If this is taken as perpendicular distance, R equal to 20 centimeter, what is the value of magnetic field? So, this is the point P where we want to find out magnetic field. So, we have already got the equation for magnetic field due to current carrying conductor. Using Ampere's law, we have derived this. Ampere's circuital law, mu naught I upon 2 pi R, where R is the perpendicular distance. Just substitute the values. Mu naught upon 2 pi, you know mu naught upon 4 pi is 10 raised to minus 7. So, mu naught upon 2 pi will be 2 into 10 raised to minus 7. 2 into 10 raised to minus 7. Because mu naught upon 4 pi is 10 raised to minus 7. Mu naught upon 2 pi is double the value. So, 2 into 10 raised to minus 7 into I 35 ampere divided by the perpendicular distance 20 centimeter. Here R is 20 centimeter. So, which can be written as 0.2 meter. So, this can be written as 2 into 10 raised to minus 1. 2 into 10 raised to minus 1 meter. So, 2 cancels. So, problem becomes very simple. Okay. 0.1. So, 0.1 can be written as 350 into 10 raised to minus 7 or 3.5 into 10 raised to minus 5 Tesla. This is the magnetic field at this point. In order to find out the magnetic field direction, you have to use right hand thumb rule, you know. So, if you stretch your right hand along the direction of straight wire, the curling of the fingers are pointing inwards. So, at this point they are pointing inwards. At the other point you can see if at a same 20 centimeter distance at the other side, it will be pointing outwards. So, magnetic field B is shown by cross mark that shows it is pointing inwards. This is one problem. There is another similar problem. There is a horizontal overhead power line which carries a current of 90 amperes. There is a horizontal overhead power line which carries a current of 90 amperes. you must have seen the overhead power lines. One wire will be live, another wire will be neutral. So, you can assume that this is a live wire carrying current 90 amperes and it is carrying the current in east to west direction. It is carrying the current in east to west direction. East to west direction. So, you are asked to find out what is the magnitude and direction of the magnetic field due to the current at 1.5 meter below the line. Suppose this is a point where the distance is 1.5 meter. The current is flowing in the direction of east to west. What is the direction of magnetic field? So, to find the magnetic field again, we have to use the right hand thumb rule. The right hand thumb rule, you see on the point which is lying on the upper side, which is on top of this, the magnetic field lines are emerging out. Whereas, you can see here the point which is lying below, the magnetic field is pointing inwards. So, here the magnetic field is pointing inwards. This magnetic field can be found out very easily using the same equation. But what about the direction? The direction is perpendicular to east-west. So, if this is east and if this is west, east, west, this becomes north and the back side it becomes south. So, magnetic field is perpendicular to this and points perpendicular in the direction of south. So, magnetic field is pointing north-south perpendicular to this, pointing inwards. So, this can be very easily calculated as we have done here. Same way, magnetic field here is due to 90 amperes of current. Current is 90 amperes and the distance is 1.5 meter. 1.5 meter. So, the problem becomes very simple. meter. So, here you can see this becomes 60. 1.5 into 6 becomes 9. So, it becomes 60 into 2. 120 into 10 to the power of minus 7 Tesla. That is 1.2 into 10 raised to minus 5 Tesla. So, this is the magnetic field due to the current that is flowing on the power line, which is their overhead power line, right. So, in the same way, one more problem is there. A straight wire in the horizontal plane carries a current of 50 amperes in the north to south direction. Now, instead of east to west, now it is in the north to south. You can take this one as north, this one as south. This is the next problem. Similar problem, the current value is not 90 amperes, the current value is now 50 amperes. The current line, the wire is in the north-south direction, the current is flowing in the north to south direction and the amount of current is 50 amperes. Give the magnitude and direction of magnetic field at a point 2.5 meter east of the wire. So, if this is north and this is south, the direction perpendicular to this will be east-west. So, if this is north and if this is south, then it will be east and back one will be west, right. So, front direction will be east and the back direction will be west. So, what is the value of magnetic field at a distance of 2.5 meter? 2.5 meter. You can take north, south, east, west. If this is north, south, this will be east west. So if you turn it, so definitely you will get perpendicular. So here it will be east and backward will be west. East, west, north, south. 2.5 meter. Same problem, only values are different. So again substitute. You see, you will get the same values. Instead of 90, it becomes 50 now. Distance is, current is 50 and distance is 2.5. So magnetic field can be very easily calculated. So thus, if you leave it, then it will be 500 divided by 25. 2 into 500 into 10 raised to minus 7 divided by 25. So 25 ones are 25, 20s are. So it becomes 40. 40 into 10 to the power of minus 7 Tesla. So that can be written as B equal to 4 into 10 to the power of minus 6 Tesla. This is the magnitude of magnetic field. So this will be, again, if it is in the north-south direction, you can see the magnetic field will be in the direction of east to west. So it will be pointing inwards. Pointing inwards, right? North, south, east, west. If it is east, west, this will be north, south. So if I am standing in the direction of north, south, front will be east. Okay. So magnetic field will be from the direction of east to west. B is from east to west, perpendicular to north-south direction. And in all these numerical problems, we have neglected Earth's magnetic field. Earth's magnetic field is also, on an average, is taken to be constant, 3.6 into 10 to the power of minus 4 Tesla, almost 0.36 Gauss. So in all these numerical problems, the Earth's magnetic field is neglected. Okay. In the next period, we will continue the magnetic effects of electric current. Okay, and we will solve more and more numerical problems. Thank you. Have a nice day. Bye.